Okay, so good afternoon, everyone. Week number 6, class number 1. Okay, we start today a new chapter related to a new device. So we started at the beginning with, if you remember the onion, starts with the core onion, very small. Onion, you know onion? بصلة. Okay, افتح البصلة حلها افتح تلقى فتلة صغيرة وبعدها فوقها طبقة وبعدها طبقة وبعدها طبقة. Okay, we started this course like that. We started with semiconductors, then we joined the two semiconductors. We made what? PN junction, and then from PN junction we made another one, and the good device, the diode. وبعدين from the diode, now we are getting to a more complicated device that is the MOSFET. Okay, good. So things are related. We will repeat many things, but as I told you, and whoever did not listen to me, it's their problem. I said, if you miss the first, you will not be able to catch the last. Continuous revision. Many of you did not do that, unfortunately. That's okay. It's their choice. But when they fail, they should not look at the mobile in my class. This is number 1. And they should not blame me. This is number 2. Okay? All right. Good. So, the MOSFET is a bit bigger device. And we'll talk about what? We'll talk about the physical structure, means how is really in real life, how it's made. We'll see how to control the current on 2 terminals by voltage on 1 terminal. Then, in this case, we have a 3-terminal device. The diode has two terminals, yes or no?
Yes.
What are they?
Cathode.
Cathode anode. This guy has 3. We'll see what their names. So, 1 terminal voltage will control the other 2 terminal current, okay? And then we'll talk about the application of these transistors in many domains, okay? And how to get linear amplification, and the basic way of building an amplifier based on this MOSFET, and the practical applications of the MOSFETs. All right, so as I mentioned before, we have many devices that are 2 terminals. What are the devices that we know that have two terminals? Diode, what else? Battery, what else? A resistor, what else? Capacitor, what else? Inductor, what else? So alhamdulillah, we have a library of devices. Now, this is the library of 3 terminals. This is one of them, the transistor. The first type, the MOSFET. We'll talk later about another transistor that is the BJT, the bipolar junction transistor. Good. The application of MOSFETs are wide and wild and crazy. Amplification in the analog domain. Analog means the signal is continuous. Change over time, continuous. So in amplification means to make this signal big. And also logic, where we need 0 and 1s. Okay, we did that with diodes. And also memories. We use also MOSFETs. Good. All right, this is one of the types of semiconductors, transistors, okay? We'll talk about its characteristics and stuff like that. And this is the simplest view. So basically the voltage on 1 terminal will control the current between this terminal and this terminal. And that's how the basically description of this transistor. Very simple. Good. So, as I said before, we have 2 types of transistors, or 3-terminal devices in electrical engineering, and that is the MOSFET and bipolar junction transistor. The MOSFET stands for metal. What is that? Metal. What is? Oxide, semi, or semi, like the Americans they like to call. Oops, not there. This one, yes. And FET stands for what? FET stands for F means field, E, effect, and T, transistor. Okay, good. So, good. So basically, this transistor works on the basis of the field effect. It means this what makes this transistor works. The field, electric field. All right? And the other transistor is called the bipolar, or the BJT. B means bipolar. Okay? Bipolar, what's that? B, bipolar. Bipolar, junction for J, and T for transistor. But there's no BJFET. There's BJT and that's it. Why? Because it doesn't use the electric field effect on its working. Good. Nice. Thank you. Very simple descriptions. But that's fine. It's good to know. We go slowly, but we go surely. Okay? All right. Good. All right. But the thing is that in real life, or in most of applications, it means if you open your mobile, that some of you use it in the class, and of course I banned that, okay, and it will be a really bad mistake to do it again. That is, if you take that mobile and break it, if you take any device from there, like a processor or anything like that, you find mainly MOSFETs. MOSFETs are the most common transistors used in electronics nowadays. Most of the electronic device, any electronic device, break it, you find MOSFET there inside. You find them in billions actually. Billions, that's how many? How many zeros are in billion? 9. Yeah, billion or giga is the same story. Okay. So 9 billion, like a few billions of transistors in the tiny chip that is less than a thumbnail. Take a thumbnail, less than that. This is how we call what we call the very large scale integration. What means very large scale integration of VLSI or other technologies? Technologies to make many, many circuits condensed in one single chip. Okay? Now, integration, what does it mean? Integration in Arabic means al-idmaj. 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 Well, indimaj is the thing that comes from you to indimaj, to become integrated. But idmaj is you make it. Okay? Now, al-idmaj, or darat al-mudmaja, okay, in Arabic. Darat al-mudmaja. Mudmaja means many circuits, we shrink them with a clever, intelligent techniques to make them in a single small chip to make something really fascinating like the mobile. Okay? So the direct mudmaja stands for what? Stands for integrated circuits. Where are that integrated circuits? Well, it's not there. I will write it here. Integrated circuits. Integrated circuits. Darat means what? Darat means circuits. How many circuits? And integrated mudmaja. So nowadays you find this everywhere. Okay? But why? Because the MOSFETs are actually smaller in size. When you make them, you can make them really, really small. Less than a tenth of a micron. Why? Extremely, extremely small. That's why you make them small. So that's why we have such a huge number of them in very small chip. And also because they are easy to manufacture. They are very easy to make them, to fabricate them. And especially this, they consume much, much less power than the BJTs. And that's why these are good for what? For the mobile. Billions of mobile now around the earth. You cannot make that kind of business if you don't have low power devices, easy to make, and very small. Okay? That's why BJT are not the ones that are used in nowadays processors. Okay? But there are applications where BJT are needed, but they are special applications, not widely used. This is it. We go now to the physical structure. How does it look like? So this is how does it look like. This is the bird's view 3D view of the transistor. So we start basically by a semiconductor. In this case, it's a p-type. Okay, it's a p-type semiconductor. Could be n-type as well, but for now, let's use this one. I'll talk about the other one. So let's start with a p-type semiconductor. On top of it, I doped or diffuse two areas. This area, okay, it's actually inside as well. Doped area of highly doped area. When we say N+, that means it's not only doped, but it's doped too much. This one, and another area on the other side, same thing. Okay, doped excessively with acceptors or donors? Donors. Yeah, donors. That's why they are N-type, okay? But too much means excessively. Very good. And then, if we take a cross-section, like this, we look, we take, and then we look, we see this. So these are the two diffusion areas, or implanted. In between them, there's nothing. There's only the body, or the p-type semiconductor that we mentioned just now. In between them are deposited, dielectric is deposited here, that you see here in white. Okay? And that dielectric, we call it dielectric. Do you know what means dielectric? Who knows? Who doesn't know? Anybody? Dielectric means insulator. It's another name of insulator used in physics mainly, but also electrical engineering. So this insulator here on top of this area that we call it the channel region, we put that insulator or dielectric, okay, very, very thin, in the range of nanometers. In the range of nanometers, not mentioned here. The next slide you will see the range. Oh, no, here. The thickness of this layer is actually anywhere from 1 to 10 nanometer. So 10 to power minus 9. 10 power minus 9 up to 10 nanometer. Very, very thin. We'll see why. Very good. Basically, we are done. The only thing remaining is that this region, this semiconductor here and here, they have on top of them a metal here, this one. It's called a metal contact. Connection, metal connection here, to connect them so that we can pass electrical current. Okay, we'll see about that. And on top of this insulator or this dielectric, there's another metal contact. Okay, and will be basically another terminal. So we have this terminal, and this terminal. We call this one the source. This one is the drain, and this one is the gate. And there's another one. That's why this device can be a 4-terminal device. 4-terminal device, this terminal, we call it the body. We can use this body for certain applications, but for you at this level, and of course in the light of quiz number 3, you do not even need to know. Just the body here now, we don't need to know it now. We just do not use it. Some applications, I use them personally. You can use the body to control also this device. But for you at this stage, no, you don't need. Khalas, you can ignore it. So we have these 3 terminals. Now, if you can see physically, the source and the drain, they are symmetrical, yes or no? Like if you look here, across this line, don't you see that this is the mirror of this? Yes. Very good. So, physically speaking, it's a symmetrical device. As you can see later, the BJT is not symmetrical. Okay. Now, that means that without connecting anything, the source can be the drain can be the source. Yes or no? Yes. Symmetrical. All right, let's keep going. All right, we are not going to read that. Yeah, one more thing we need to read. We mentioned the channel region. This channel region has a length of L and the width of W. Remember, the width means how wide is this, and the length between the two diffusions. Okay. All right. This device, or this transistor, we call it NMOS, N-type MOSFET. Why? Because basically the source and drain, they are N-type. Or later on, or soon today, we'll discover also the channel that goes actually here is an N channel. That's why we call it N-MOSFET. N-MOSFET. Or because humans are lazy, not only me, animals, and that's it. FET, we know that's a FET. خلاص? All right, good? Good. Excellent. That's it. So this is just, you know, a description. Okay? Don't worry, we'll get to the other stuff. So the name of SET, the name of the MOSFET is derived from the physical structure. Why? Because basically, if you are aware, if you are jumping, if you imagine yourself like this, looking around, looking on this direction, when you look here, you find first, what do you find?
Metal.
The metal, so M. And then after that, what do you find? The oxide, O, Mo. And then what you find next? Semiconductor. That's why we call it MOS. So if you look at here, that's the structure. So basically, this is the most important region of the MOSFET. Okay? The most important region of the MOSFET. Means where the business is taking a place. Where the business of the functionality of this device will take place. Okay? Good. For PMOS, again like we did with N-type and P-type, we just flip. Right? What does it mean, flip? So instead of P-type substrate, we will have an N-type substrate. Yes or no? And instead of an N-type, an N-plus diffusion drain, we'll have a P-plus diffusion drain. Same thing what? With the source, P-plus. And the rest, that's the same. There's no semiconductor here or there. Stays the same. And in this case, we have the PMOS. Don't worry, we'll come back to it. Okay? This is to show you. Really, electrical engineering is nothing but a game. If you take it that way. Just need to be serious game, and you will enjoy the game very, very much. Okay, keep going. We already explained that. However, at some point in time, the MOSFET, the metal has been changed with another material. We call it polysilicon. Okay, polysilicon is a material. Semiconductor, I'm not sure if it's semiconductor or not, but it's a material that sometimes gets replaced the metal on top of the gate only, okay? So don't be surprised to find this kind of contacts on top of the gate, okay? But it doesn't change anything because the metal is nothing but to make a contact. Before we go further, let me remind you about something. We did a device, we did a diode that is composed of metal and N-type semiconductor. What is that diode?
What's that?
A diode that is made of a metal and a semiconductor. N-type. Which diode is that called? We did it also last week. That means really those who revised are very minimal. No one has revised, I'm sure. Yes, that? Tell me.
That when the light is...
There is no light about this. It has nothing to do with the light. But that's fine, keep trying. That means the vision has not been taken. We did not revise. You cannot succeed with this way. No, seriously, we need to be serious. It's the first diode we studied. It's called the Schottky diode. Schottky barrier diode. Remember?
Yes.
See? What is the revision? Gone in the party. So please, revise. When we have always a metal on top of an N-type semiconductor, we have a diode. But here, the fabrication process kills that diode. They try to not make that diode exist. And that's why they make what we call ohmic contact. Here, here, and of course here. But here is not big deal because the insulator is not semiconductor anyways. So here, these contacts, they are called ohmic. Why they call them ohmic? Because Mr. Ohm did say that, you know, if we have a resistor, we can have an Ohm law there, right? So here, so there is no diode basically. The ohmic contact, it means that the diode has been killed. It has been destroyed by the process of fabricating these contacts so that they are ohmic contact, means they are just like resistive contact, okay, to make the connection between our terminal and our semiconductor, okay? It's a special process. Not complicated, very simple, okay? So we don't have what? We don't have the the Schottky barrier diode or Schottky diode in short. Okay? So here we do not have that one. What else, sir? There are other assumptions that we need to make sure that are respected. What are they? Okay. So that. Now, another name also for MOSFET is also IGFET. This is another name. IGFET, I means what? Insulated or isolated. Let's say insulated. And G means gate. Why? Because the gate has no contact with the channel zone. Yes or no? Because there's an insulator. Yes or no? That's why we call it insulated. There's an insulator between the gate terminal and the channel. So there's no current that can pass through. Good. All right. Okay. Very important condition here is that you can see here in the structure of the MOSFET that we have here, what we have here? We have here a diode, yes or no?
Yes.
And we have here also another diode. And this diode is not only here, it's also here, like all around. See? All around is a diode, yes or no? So the diode is actually all this, not only here in this place. Some people, they think that way. No. The whole thing is a diode. Same thing said here. Okay, good. So the condition, so here what we want in this MOSFET, we want the current not to pass on this red line. Means not to pass through the body. We don't want this. That means what? That means we need this diode and this diode always reverse biased. Okay? Because if they are not reverse biased, it means the body voltage is higher than these, then the current will go from the body to the terminals. Yes or no? But here for the MOSFET, we want the connection or the current to pass through the terminals. This is the direction of the current. Not from here. If these diodes are forward biased, then the current will come from the body. Yes or no? We don't want that. We want the current only to come between the source and drain, not between the body and the source and drain. Means this current, okay, this current should not take place. This is not allowed, and this not allowed. And to make that happen, we need this to be reverse biased and this reverse biased. So that the only current that we need to create is through the channel. We'll see how. So if we make these back-to-back diodes, this back-to-back, no, this is the back of the diode, this is the back, so back-to-back means that their backs are connected. Okay? So in a summary it's like this. Okay? In summary it's like this. So this is what? This is the body, B. This is the, for example, drain in this case, and this is the source. And on top of here, if you want, this is not true, just to show you something here, you have here a gate. So a gate through a capacitance here will connect the cathode of these diodes, okay, and make the current pass how? Pass between these. This wire, not this wire. The body should not have any business with this current. Nothing should pass between the body and the source. And this is just to explain. So this is what? I will write it in red. This is illustration. It means it's not official. It's not real. It's just to explain how this thing works. All right? This is just for illustration. Okay. And therefore, the resistance here, because it's reverse biased here and there, so basically the current is extremely small. So that means the resistance here is extremely high. It's in the tera ohm. Tera is not 9, it's 12 zeros after 1. Huge. That means there is no chance for the current to pass through the body between the source and drain. Okay? Good. All right. Any question? You should stop me when you need to stop, okay? This is your course. It's you who need to understand, not me. Good. Let's play a game with this transistor. Let's connect the source and drain and the body to the ground. Means there is no voltage there. And then let's put some voltage on top of the gate. Okay? Remember that even before we put some voltage in here, we have a depletion region between the N and the P, between the cathode and the anode of the diode. Yes or no?
Yes.
So initially we have this region here that we call it what? Depletion region. Depletion region, that means there's no free carriers in that region. Yes or no? Initially. So what do we do now? We just do this game. We increase the voltage of the gate. Increase the voltage, or it's as if we put positive charge. In real life, we don't have positive charge moving, yeah? But here we are talking about electric field, so effectively we are putting positive charge here. Okay? All right? Good. So when we do that, this charge, they will create an electric field through the insulator. Yes or no? I will draw it in red. That electric field, which direction will go, up or down? Down. Very good. So this is gonna be the electric field. And thanks to the thickness here of this insulator, thickness is so small, the electric field can go through. Okay? So that electric field, what does it do? Here in this area, okay, here at the beginning we will have the depletion region here in the green, here, all around, and here too. Yes or no? But then this area was not depleted, yes or no? It has majority carrier what? P, holes, right?
Yes.
So the electric field will do what for the holes?
The holes will move in the same direction as the
That's right. So the holes, let's put that in red, they will be pulled away from the channel, yes or no? They will move out. What about the electrons? The electrons, if they are what? They are what here? Minority carriers.
will move up.
Will move where?
With the
Will move up.
Opposite the
Opposite.
the
Yes. Where do they go? They go just beneath or تحت وين? Under the insulator here, right under the insulator. Okay. So that electric field will bring more electrons to it. Will push away the holes. Okay. So meaning that after a certain time, this zone under the channel will be also depleted. Yes or no? Either they go up, the electrons, or the holes will go down, but the region will be empty of charge. Yes or no? And we call it what? A depletion region too. Yes or no? This also will be depleted. And that's why we need to clean up the end. So basically we have a depletion region all under this area. Okay. So this is when we apply a small voltage, small voltage on the gate. Good. So let's continue the story. So this is what we said, and then what happens, sir? The electrons now, they get accumulated where? Under the insulator here, and also we have electrons also in this area and in this area. Okay? Good. We are not going into details, you can read them here. But this electric field, if we keep increasing it, that electric field will be able also to attract the electrons from the diffusions, from the source and drain. And will attract also more of them from the p-type, because as we increase the field, the depletion region also will go deep. So we'll collect more electrons, yes or no? So the density of the electrons here will increase, keep increasing as we do increase the gate voltage. Correct? Good. Yes?
It will not cancel the positive charge and negative charge.
No. Why? Because we have insulator. Remember this. Remember, we have a very good question. Listen, there is no stupid question in my class. All questions are welcome. All mistakes are welcome. Okay? So, remember here, we have what here? Remember, I'll draw it in red. We have here an insulator. Unfortunately, the colors are not helping. We have here an insulator. Remember this? The dashed area here? They cannot touch each other. Okay? So it's like a capacitor. We have N charge, we have insulator, and we have another charge. صح ولا لا? This is capacitor, yes or no? We are creating capacitor between the gate and the channel. Yes or no? You understand? So they cannot touch each other because the insulator will stop that. They cannot. Okay, we'll push them away. You understand? Good question, good question. Nice question. Good, very good. So, and then what happens? And then the density of these electrons will be high enough to make the electrons in this area under the insulator not p-type, but it will be n-type. Means the majority carriers here under the insulator will be not the holes like the beginning, will be electrons. Then we will have what? Is as if we have an n-type semiconductor here. So we have n-type here, n-type here, and n-type here. That means here we have basically a channel between the two terminals here. It means if we have anything, if we have any current here, if we increase this voltage, we create a current, that current will pass easily to the other side. Why? Because this channel allows it. There is nothing that stops. There's no barrier here. Yes or no? See? Now we create a channel. What means a channel in Arabic? Ana, exactly. You know how? This is like what? For those who like agriculture like myself, it's like some people between two lakes, between two swamps in the garden, and you try to dig a little bit of channel to make the water move from one side to the other side. From the river that has more water to the tree that has no water. We have high voltage. This is higher than this. The water will pass. Yes or no? That's what it is. This is what it is. You create a channel. It's like you are digging a path for the charge to move from one side to the other. But to have a charge, you have to have a voltage here. You have to have a water here to pass. Yes or no? That's what it is. Okay? So you create the possibility for the charge to move from one side to another. Or what you need to have a certain charge here or a certain voltage here to pass, to go easily from this to that. That's it. So this is, in a nutshell, in a very simplistic way, what is the functionality of this. I will not read this. And then here, basically, if we create a certain voltage higher here in the drain, that it will create a current that goes to the source. But by the way, why we call it a drain and source in the first place? Drain in Arabic, what does it mean? Balu'a. When you clean at home, the water needs to go somewhere, yes or no? When you take shower, the water needs to go somewhere. It goes to the balu'a. Balu'a is the drain. But the problem here, the current is going from al-balu'a. It's not going to the balu'a. Mafrood current going that way. The currents actually are movement of positive or negative charge. Positive charge. Yani the positive charge will move this way. Yani the electrons will move from where? The opposite way. Now, al-balu'a makes sense. Yes or no? It's the drain of the currents of the electrons. It's the drain of the electrons. The electrons go to the drain. But the current goes from the drain. Comes from the drain. Do you understand?
Yes.
Okay? That's what it is. And the source is the source of the electrons. Okay? Is where the electrons will come from to go to the drain. That's why we call this balu'a, drain. Where the electrons will go away. Okay? Because the electric current is the opposite to the motion of the electrons, is opposite to it. Remember that? That's why we call this one a drain, and this one is the source, remember? Okay? And the MOSFET is like what? It's like Hanafiya. It's like you open, you let the water go, or close, and stop the water from passing. Good? Not like the one that you turn, actually. There is the Hanafiya, you press, yes or no? This is the one that you press, similar to this. You press, you create a channel, boom, it moves. Yes or no? You take away, and the channel doesn't exist, and bye-bye. That's exactly like that. Nothing more. Simple or not? It's a joke. It's not only simple, it's a joke. So, do not take it really very hard. Now we come to the business of equations. So we go step by step to understand how this nice device works. Because as an electric engineer, I need to know that to do things or to explain things. Okay. There are parameters that we need to describe and define them. The first parameter is the threshold voltage. What is the threshold voltage? The threshold voltage is the voltage above which the gate voltage need to be to create the channel. يعني, if the gate voltage is below the threshold voltage, there is no channel. Do you understand? Here is the minimum voltage of VGS. Here, why we call it VGS? Because the source is always grounded. It's actually the lowest voltage, okay? The source. Do you understand? Because if you remember, like the battery, this is where the electrons are coming from, yes or no? So this is the source. You understand? Same thing for the MOSFET. The source is the lowest voltage. That's why we refer to it as VGS, not VG alone. And VGS means what? Remember this? We'll repeat that again. VGS is actually VG minus VS. So it's the voltage with respect to the source. Okay? Okay. Two students are discussing during class, and they are disturbing others. I advise them not to do that anymore. Okay? Next time I will ask them personally. Okay, good. So this VGS, if it increases above VT, there will be a channel. Below that, VT or threshold voltage, there will be no channel. It means we did not create an N-type under the insulator. Yes or no? Good. The value of that VT or threshold voltage is between 0.6 and 0.3 volt. It's quite small. Okay. This is by the manufacturing. This is how the manufacturers of the MOSFET, they can, control this value, but for us it's constant. Okay. Field effect, I'm not going to talk about that. Khalas, we discussed it. Now, the other parameter that is really important is the overdrive voltage. We don't use effective voltage much. We use the word overdrive. And what is the overdrive? It is actually, let's say VGS, let's say is this. Okay? And let's say this is VT. VT also is with respect to the ground, which is S. Let's say this is VT. We call this is VGS, huh? VGS. Huh? And this is VT. This voltage, VGS, the difference of VGS above VT, we call it V overdrive. You understand? It's the difference between the VGS and the threshold. It's defined always above VT. Means if VGS is equal to VT, V overdrive is equal to 0, there is, that's at the start of the channel. It's not created yet. Now, as VGS becomes above VT, now the channel will exist and will increase. Okay? We'll talk about that in a second. Okay? So the overdrive is the voltage above which VG is above VT. Okay? هو الفرق between gate voltage and threshold voltage. بس overdrive. Alright, what else we need to define? We need to define the oxide capacitance. Oxide is the insulator, is the one that is between the gate terminal and the channel. That's an oxide. Oxide, and basically its chemical composition mainly is SiO2, silicon dioxide. Okay, that's the insulator that is mostly used as an insulator in the MOSFET. Okay, good. It has what you call a capacitance per unit area. Okay, means capacitance divided by area, or the density, the areal density, and its value is equal to epsilon ox permittivity. Remember permittivity?
Yes.
Okay, divided by T ox, which is the thickness of the transistor. Okay, and of course, because it's capacitance per unit area, so the unit will be farad per meter square, or per centimeter square, or whatever unit you like to choose, but it has to be something meter square, something like that. Okay, good. All right, good. All right, so okay, blah 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 blah. Okay, good. All right, so we need to know we need to establish the first relationship between the voltage of the gate and the current that pass through. This is very important. Same thing, always IV characteristic of any device, we need to know if it is a resistor, it's Ohm's law, we know how to draw that. If it is diode, it's exponential, we know how to do that, or other models. Here also same story, we need to do the same thing. How to do that? The first step is to estimate how much charge we have in the channel. For the small values of VDS, means VDS is quite small, between 0 and certain value, we'll discuss it later. The charge under the, so basically we have, this is the transistor if you, okay? Let's do that, okay? So we have the channel is like this. This is channel. Here we have what? Electrons, yes or no?
Yes.
Very good, very good, very good, very good. We have these charge, or these electrons. Here we have the source, the drain if you want, and this is the source, just to say this is grounded only, that's it. That's it. So here, to estimate the charge in here, we know the thickness here of the oxide, Tox. Yes or no? And what else? We know the voltage, okay? We know the voltage between the gate and the channel. The voltage of the channel. The voltage of the channel is equal, basically the charge in the channel will feel the overdrive. It means every single part of this channel, every single charge here, will feel the voltage, the overdrive voltage. That is the voltage of Vg minus Vt, means the above Vt. Below there is no channel. Above we have that voltage that each charge here will feel. So basically, if I want to calculate the charge here in the in the channel, so basically what I need to do, I need to basically apply the capacitor charge equation. Q is equal to CV. So the voltage here is going to be the overdrive voltage, because that's the voltage, effective voltage that this charge will feel, and C is going to be Cox. But I have to multiply by the dimension. Remember, Cox is the capacitance per unit area. So I have to take that and multiply it by W and L, which is the dimension of the transistor. Yes or no?
Yes.
Very good. So W multiplied by L will give me the area here of the gate. Multiplied by Cox will be the capacitance. Multiplied by the voltage of the channel, which is the overdrive, I get this equation. See? Cox, WL, the overdrive. Bingo. This is the charge when VDS is not too big. When VDS is small but positive and is there, so we have this charge. So, if the overdrive increase, the charge will increase. Yes or no?
Yeah.
Because if the overdrive increase, that means the electric field will increase. So I'll collect more electrons. Yes or no? So the channel will become bigger and bigger. It means I will be basically digging the earth more and more, so the water can pass more and more, yes or no? So the channel becomes deeper and deeper, yes or no? That's what it is. So the charge means the amount of water that the channel will be able to carry will be higher, yes or no? Instead of a little bit of water passing through, I will have lots of water that can pass through, yes or no? You will see that in a second, okay? And that's what this equation shows. Good, almost there, almost there. Now to calculate the current, oh wait a second, maybe I did pass something, no. Now to calculate the current, this is the equation of the current. To see how we get this current, it's very simple. What's the definition of the current? ID is basically IDS. ID means IDS. It means it's the current ID that goes from the drain to the source. So that means the drain voltage is higher than source voltage. Some of you still make the mistake that the voltage will go from negative to positive. Unfortunately, this is a terrible mistake. Anyways, so the definition of ID, because S is ground, so who care about S? I can throw it and just call it ID. So it's actually dQ, the change of Q with respect to time, yes or no?
Yes.
So what if we do multiply by DL and divided by DL? We can do that, yes or no? And then I take this. This is what? This is nothing but the velocity, yes or no? But here, the velocity of what? Of the charge that passed from the drain to the source is actually drift velocity. Yes or no? Because of that voltage between the drain and the source that makes this. Yes or no? It's not diffusion. It's drift. Yes or no? And dq over dl, what is it? Is actually the density, the linear density, الكثافة الخطية of what? Of the charge. Yes or no? In the channel. How many charge per unit length? Very good. Excellent. Now, if you remember, the drift velocity is equal to mu n times
V.
times the electric field. Yes. Mu n times the electric field. And you know that the electric field is actually the difference of voltage divided per unit length. Yes or no?
Yes.
And that's what it is. VDS divided by L, which is the length of the channel. So this is the electron drift velocity. And this is what? This is the charge per unit length, or the linear charge density. Why? Because if you remember, the charge was equal to what? C ox W over L, V over drive. So if I do this, dl, or divide by L, because it's uniformly distributed, I just get this out. Yes or no? So the remaining would be C ox W, V over drive. Now let's see. C ox W, V over drive. Yes or no? That's it. This is how the beauty of electrical engineering. But don't worry, the derivation is also mentioned in the next slides. Okay, it's also there. Okay, so this is Q over L that we just found, and the electric field in absolute value. Because usually, typically, there's a minus here. Yes or no? Yeah, that's fine. We took just the absolute value. That's it. And the velocity, the drift, some of you forgot that, is mu and E we replace this there, and that's it. And this is the beauty of units. When we replace these parameters with the units, we find that the unit of this is nothing but meter over second. That means, yes, we are dealing with velocity. Some of you still make the mistakes of the units, and they think 5x is equal to 5 watermelons. Units are important. Why? Because they protect you from making mistakes and to have the exact value. Like 1 kilo is not the same like 1 mega. Do you understand? Give you a sense of measure. Good. We're not going through this. We're going close to end of this class, okay? So now what we did nothing actually. We have done nothing except that there was over L here. Yes, sir? Remember that? And mu n was here. Yes or no? So mu n, we bring it here. And we took it off from here. Yes or no? And L, we brought it here. Oh, we brought it here. And we got rid of it here. Yes or no? That's it. So, putting parameters together. Why? Because it helps us to do stuff. Okay. Now, we have a constant parameter that is independent of anybody else except the manufacturer. This comes from the manufacturing. And that's why we call them process. Process means is related to manufacturing. تصنيع or معالجة if you want. Okay? Okay? So this is related to manufacturing. We'll get to that in the next slide. Okay? These are constant that are related to the process, and they are called process transconductance parameter. Transconductance means they are responsible of creating the conductance between the drain and the source thanks to the gate voltage. So the gate voltage creates this current between the drain and the source. That's why it's transconductance. It's the conductance that created, transferred between the gate to the drain and the source. Good. Very good. That's it. So that's one. Okay. Now we come to play some games in here. Now, if you remember on law, if there's a current and there's a voltage, who creates this current actually? It is not this one. Creates this current is actually this guy. Yes or no? Because overdrive creates just a channel, doesn't do anything else. but who creates this current is actually VDS. That's why here it's a linear relation or not. Yes, it is a linear relation. That's why I can write that the resistance between drain and source is equal to VDS over ID and is equal to 1 over these parameters. So, in summary, what's that? Okay. You can read this at home. Okay, what is that? Okay. So now, these parameters, as we mentioned before, mu and Cox, we replace it from now on with Kn prime. It's called the process transfer conductance parameter. This is related to manufacturing. This is by the manufacturer, okay, who make these things. He will give you these constants, okay? Now, W over L is called the aspect ratio. It's you who designed that. So you as a designer, you come here, you specify the W over L, okay? But they will not change after that. Once you're done, they're done. Now, the last parameters, that is, the last parameter, which is the overdrive, that is a voltage dependent on the circuit where you put this MOSFET. So that's why we call it application parameter or circuit parameter. Depends on the circuit how much you put voltage there. So in a nutshell, the resistance is equal to, let's say, is it written here? Let's see, oops, no. So, is it the graph? Yeah, okay, fine. In any case, it's not written here. We can write it again, that's fine. So RDS is equal 1 over Kn prime, yes or no? W over L, yes or no, designer? And V over drive, yes or no? This is in summary. You go back and you find it. So now, if I draw the slope of ID versus VDS, this is the ID VDS or the IV characteristic of the MOSFET. If I draw that, I will basically draw the relationship between ID and V. You know that ID is equal, when VDS is small, not too big, is equal to VDS, yes or no, divided by RDS. So it's a line, yes or no, with a slope of 1 over RDS, yes or no? Now, RDS, okay, these graphs like you see here, each one of them correspond to a certain overdrive. Here the overdrive, the overdrive is 0. Here it has a certain value, here a certain value. As we increase the overdrive, what happened to RDS? Decrease. Ah, very good. RDS decrease. But 1 over RDS will increase, you see? So, as we increase the overdrive, okay, what happens to the RDS? It does decrease, and because RDS decrease, the slope will increase. Yes or no? The slope is increasing this way. Yes or no? Slope is increasing this way. Yes or no?
Yes.
Is increasing. Why? Because the resistance decreased because the overdrive increased. So the overdrive decrease RDS, and the decrease of the RDS increase the slope. يعني, in a summary, the overdrive will increase my slope. In a very short summary. As we increase the overdrive, we increase the slope. And consequently, we decrease basically the resistance of the channel. Alright, that's it for today. Inshallah, next class, we'll have our 4th quiz and we'll continue this chapter. Thank you very much.